Welcome to the talk of garment capture and synthesis for real-time virtual try-on. In this talk, we discuss our system for live virtual garment try-on. And hi, thank you for coming. I'm Toby Chung from the University of Tokyo. I'm a first-year PhD student under the supervision of Takeo Igarashi. Virtual try-on, which allows you to try different garments virtually, is important for two main reasons. First, we're shopping for fashion items online more and more often these days. And when we do that, we don't really know how a piece of garment would look on our body before we actually get the item days later. And secondly, with virtual conference being more and more popular than ever, many people are looking for a solution in which they can attend formal meetings in the comfort of their pajamas. Existing work that attempts to address the problem. These methods replace the garment of a user in an image, given another different garment reference. However, there are a couple fundamental limitations that prevent this method from being practical for live try-on, namely limited dataset and the lack of size reference. First, these methods are often trained on professional model images, which only include a very small range of all possible motion during virtual try-on, which does not cover the rich motion that people actually do when they actually try to test a piece of garment. Secondly, and arguably more importantly, these methods fail to capture the size of the garment. Trained using only a single image of garment without the size information of either the garment or the fashion model, most methods do not have the concept of size and cannot generate accurate size of the garment on the user's body. This is especially problematic when it comes to virtual try-on for online shopping, where the shopper is offered multiple size options and has to decide which one they prefer. Based on the limitation that we observe, we introduce a virtual try-on system that allows real-time interactive garment try-on. And here are some of the results. Here is the overview of our method. Our method can be broken down into two main parts. Try-on, which is where we generate the result of the user in a different garment in real time, and capture, where we prepare the data for the try-on part. Our key contributions are first, we designed a mannequin robot that allows us to capture garment extensively. And second, we designed a proxy measurement garment that will provide a size reference for the user. We first designed and built an actuated mannequin with 9 degrees of freedom. It's made of 3D printed outer shell and a sheet metal internally. This mannequin can rotate and move its arms to mimic different poses that a person would do during actual try-on. Additionally, the mannequin can change its shape into different body configuration. With the mannequin, we can capture garment deformation under different body pose and shape. For each piece of garment, we rotate the mannequin and change the arm position and body shape and capture 80,000 images for the garment. This process takes approximately 2 hours, and this process is mostly automatic except at the beginning where we have to put the garment onto the robot. We also design what we call a measurement garment. A measurement garment is what a user has to wear to use our system. It's a color-coded t-shirt which marks different parts of the user's body. We designed the measurement garment to be something that we can easily extract from a video frame, and it's something that is easy to put on and it should retain the body pose and size information. We tested a couple designs of the measurement garment before arriving at our current version of it. The measurement garment that we designed is inspired by segmentation visualization and is designed to be bright such that it's easy to be seen even under darker indoor environments. Now that we have introduced all the core building blocks of our system, we can talk about how we prepare the data required to produce the virtual try-on result. First thing we need is to capture the measurement garment. This happens only once, and we can reuse the same data for any new garment that we want to provide try-on for. To generate a virtual garment for a new piece of garment, we need to capture the garment using the mannequin robot. And finally, we use the data to train an image-to-image translation network, which takes approximately 2 days. We capture paired data for the measurement and target garments, which are the data under the same body pose and shape. We then encode the measurement garment to our segmentation map using k-means. Then we adopt network architecture from Pix2Pix HD to train a network to map the segmentation map to the target garment. Conceptually, we basically learn a mapping function that converts the segmentation map of the measurement garment to the target garment RGB values. And we train it using both adversarial knot loss and feature matching loss, as described in the Pix2Pix HD paper. And this concludes the preparation process of our system. And that brings us to the try-on part of our system, where the user wears the measurement garment, stands in front of the camera, and we generate a virtual try-on result for them. We do so by first separating the measurement garment from the frame using a semantic segmentation network. After removing the body and the background, we apply k-means to the measurement garment to obtain the segmentation map. We then pass it through the image-to-image translation network that we trained earlier. We can load different network weights at runtime to dynamically change the virtual garment in real time. And finally, we can recompose everything, including the background and the user's body and the garment, together to generate the final result. Here, we show a couple example results generated using our system. Additionally, we also show results generated using an existing method, ACGPN, which uses only static particle image as the garment input. We evaluate our method using a couple studies. First, we conduct a user study where the participant can try our system and provide feedback. Second, we also ask the participant to identify the size of the garment that they prefer using only our system. And finally, we test whether our system is robust under different lighting conditions. For the user study, we recruited 8 participants and they were able to test 10 virtual garments in total. 5 of the garments are of different designs, and 5 of them are all the same, but they are of different size. The user study feedback is generally positive, with the participant finding the system very useful and provide realistic results. We also asked the participant to test a virtual garment of 5 different sizes and tells us what size they prefer using only our system. After that, they have to try the garment, the physical one, and tell us which one they prefer after they actually put it on. With a proper reference of size using the measurement garment as a proxy, our method can produce accurate garment size relative to the user's body, while the baseline method, ACGPN, cannot. 7 out of the 8 participants correctly identified the size they prefer using only our system. Our method can also be applied to video conference application where only a portion of the upper body is visible. In summary, we introduce a real-time interactive virtual try-on system using a data capturing mannequin robot and a specially designed measurement garment. You can learn more about our project and obtain some of the data from our project page. Thank you.